work energy theorem and its applications. The work energy theorem gives the relation between work done on a particle and change in kinetic energy. What this work energy theorem states? The statement of work energy theorem, that is, the work done on a particle by the net force is equal to the change in its kinetic energy. Work done on a particle by the net force is equal to change in its kinetic energy. Here, two kinds of forces we are going to discuss. One is a constant force act on the particle. What is the proof of work energy theorem? If a variable force is acting, the proof of work energy theorem. The first one is, if a constant force is acting on the particle, the proof of work energy theorem. For that, let us consider a particle of mass m moving with initial velocity u. On this particle, a constant external force F is acting along this direction. When some force is acting on the particle, acceleration is produced in this particle. That acceleration is uniform acceleration. Why? Because the force acting is constant external force. Due to that constant force, the acceleration is constant acceleration. Nothing but uniform acceleration. Acceleration is there in the particle means its velocity changes. What is its initial velocity? U. Now, after traveling s displacement, its velocity becomes to v. Its velocity becomes v after displacement of s. Here to here particle displaces. Here its final velocity is v. Now, we are going to find the work done. To calculate work done, here by the constant force, the work done W is equal to F dot S, magnitude of the force and displacement. Now, force. From Newton's second law, F equal to ma. Then W equal to mas. Since F equal to ma, this is from Newton's second law. What is A here? A is the uniform acceleration of the particle. Its initial velocity u, final velocity v, displacement is s, and the acceleration is a. The equation of motion which relates these four quantities are v square minus u square equal to 2as. From here, the a, acceleration of the particle, is v square minus u square by 2s. Now, this acceleration substitute in this place of a. Then, W is equal to m into v square minus u square by 2s into s. S cancel. Then W equal to half mv square minus half mu square. What is half mv square? Half mv square is the final kinetic energy of the particle. Half mu square is the initial kinetic energy of the particle. Why? Because v is the final velocity, u is the initial velocity. Work done equal to final kinetic energy minus initial kinetic energy. W equal to kF minus Ki. What is Kf and Ki? Kf and Ki are final and initial kinetic energies of the particle. Now, Kf minus Ki is the change in kinetic energy of the particle. What is that equation there? The final equation is W equal to Kf minus Ki. What is W? work done by the constant force, is equal to Kf minus Ki is change in kinetic energy. Hence, work energy theorem is proved. This is by constant force. Now, by variable force. Work energy theorem for a variable force. If force is varying means the acceleration of the particle is not constant. Acceleration is not constant means velocity also changes. So, in this case, the work energy theorem means work done is not able to find by using W equal to Fs formula for variable force. So, here to find the proof of this work energy theorem, let us consider one-dimensional motion of a body of mass m which is acted upon by a variable force. If at any instant of time, the speed of the body is v, then at that instant, the kinetic energy of the body, mass is m, velocity is v for the given instant of time, then its kinetic energy is half mv square. K equal to half mv square. Half, numerical number. M, mass of the object. V, velocity. Here, the variable force, acceleration is not constant. Means, velocity is also not constant. If velocity is not constant, now I am going to find rate of change of kinetic energy, dk by dt. For that, I want to differentiate this equation. So, the rate of change of kinetic energy is dk by dt is equal to half m constant for v square 2v into dv by dt. 2 cancel, this part left there. M into dv by dt into v. What is dv by dt? Rate half change of velocity. Rate of change of velocity is acceleration. This is acceleration. Into v. What is v? Velocity. Velocity is defined as rate half change of displacement. Rate of change of displacement is velocity. So, instead of this v, I am using dx by dt. Instead of this dv by dt, I use a. Here ma is force. Whatever the variable force is acting, that is ma. Here dt cancel. The change in kinetic energy dk is equal to ma into dx. By integrating that, we get total work. Integrating on both sides to get work done. That is, integral dk is equal to integral f dx. What are the limits? For initial position, the kinetic energy is k1. For the position x5, that is kf. Kinetic energy is kf. Now, integral dk is k. After substituting limit, k final minus k initial is equal to integral f dx within the limits xi and xf. Initial position and final position. What this part states? This is work done by the variable force. Net work done by the variable force. Hence, change in kinetic energy is equal to net work done. Work energy theorem is proved in case of variable force also. This is work energy theorem. It states that work done by a force acting on a body is equal to change produced in the kinetic energy of the body. This is work energy theorem. We proved this work energy theorem in both two cases. One is if the applied force is constant force, if the applied force is variable force. Now, no. This theorem is not only applicable to a single particle, but also for a system. A system means number of particles starts from 2 or more than 2 particles are there, that we called as a system. When it is applied to the system of 2 or more particles, the change in kinetic energy of the system is the work done on the system by the external as well as internal force. That means the work done by all the forces, whether it is external or internal. If you apply this work energy theorem for a system, the total change in kinetic energy of the system is work done on the system by the internal and external forces. Now, the next point. Work energy theorem is also applicable to a system under the action of variable force, constant force, conservative force and non-conservative force. For all kinds of forces, work energy theorem is applicable. Now, applications of work energy theorem in various situations. The first situation is a particle of mass m is thrown vertically up with a speed u, neglecting the air friction. Work done by gravitational force as particle reaches its maximum height. What is initial velocity? U. U is the initial velocity. Then a body projected upward with initial velocity u, when it reaches the maximum height, at that point its velocity becomes 0. Velocity at the highest point is 0. Velocity at the highest point is 0. Then work done is equal to change in kinetic energy. What is that? Work energy theorem. Work done. It rises to h maximum height. mgh is the work done, which is equal to kinetic energy final becomes 0. Kinetic energy initial is half mu square. So, work done is equal to change in kinetic energy. This principle we used for this example. That is this one. Now, the next application. A block of mass m slides down a frictionless smooth inclined plane of inclination theta to the horizontal. If h is the height of inclination and the velocity with which the body reaches the bottom of the inclined plane is, here the block is placed on the inclined plane. Theta is the angle of inclination. H is the height. Here onwards, the object starts with initial velocity 0. While reaching the ground, what is its velocity? V. Now we are going to find this V value. Now we apply work energy theorem. What is work done? What is the displacement caused in the body vertically? Vertically initial point is this one. Final point is this one. In between these initial and final point, the displacement is h. Work done is mgh. Now, what is initial kinetic energy? 0. Final kinetic energy, half mv square. So, mgh equal to half mv square from work energy theorem. Work done equal to delta k, change in kinetic energy. mgh equal to half mv square. From here, v square is equal to 2gh. v equal to under root 2gh. What is that? Velocity of the block when it reaches bottom of the inclined plane. This is second application. The third application is a bullet of mass m moving with velocity v stops in a wooden block after penetrating through a distance x. If F is the resistance offered by the block to the bullet, what is the resistive force acting on the bullet by the block? That is Fk. Then work done by the resistive force equal to change in kinetic energy. What is work done by the resistive force? Force is Fk. Displacement of the bullet from here to here, that is x. Then the work done is minus Fk into xy negative sign. Fk direction is this one. Displacement is opposite to resistive force, 180 degrees. That gives this minus sign is equal to. Finally, the bullet stops. Stops means final velocity is 0. When final velocity is 0, final kinetic energy is 0 minus initial kinetic energy half mv square. Its initial velocity is v. So by using this, we calculate resistive force or distance travelled by the bullet before coming to rest inside the block. So we calculate all these. F is equal to Fk. So Fk, resistive force, becomes like this, mv square by 2x. This is one more example. Fourth one. A bullet of mass m is fired horizontally with a velocity v, which strikes a wooden block of mass M suspended vertically. So here this is the bullet whose mass is small m, moves with velocity v. This bullet strikes a wooden block, this is wooden block, which is suspended from a rigid support vertically. The mass of this block is capital M. Now, if bullet is embedded in the block, so bullet hits the block and embedded in it, then the height h to which the system would rises. So now we are going to find this h. For that, here we have to use two principles at a time. What are the two principles? One is work energy theorem. One more is law of conservation of linear momentum. Law of conservation of linear momentum application. Here observe. Bullet is under motion. Initially the block is at rest. Means initially only bullet has linear momentum. What is linear momentum of bullet? mv. After hitting the block, the bullet embedded it inside the block and the total combined system means block along with bullet, moves along this direction with v1 velocity. What is law of conservation of linear momentum? Total momentum before hitting is equal to total momentum after hitting. No external force acting, then total linear momentum remains constant. We apply that rule first. Then from principle of conservation of linear momentum, mv is the initial momentum, which is equal to capital M plus small m into v1. From here, mass is small m. Here this one is small m. Then mv is equal to capital M plus small m into v1. Here v1 equal to mv by capital M plus small m. What is v1? Common velocity of both the block and bullet. Here v1 is the common velocity of the bullet block system. Now with this v1, it rises to a height h. This is the maximum height, means at this point the combined mass velocity is 0. Final velocity is 0. What is initial velocity for combined mass? v1. Change in kinetic energy is final kinetic energy 0. Initial kinetic energy half capital M plus small m into v1. Work energy theorem. Work done by gravity equal to change in kinetic energy. Minus capital M plus small m into gh is equal to final kinetic energy 0 minus half into capital M plus small m into v1 square. Here h is equal to capital M plus small m. Here cancelled. H becomes, this g comes to here, minus minus cancel, 1 by 2g into v1. What is v1? mv by capital M plus small m. Substitute here mv by capital M plus small m whole square. This is the height of the combined mass raised. MCQs. the total work done on a particle is equal to change in its kinetic energy. What is this? This is only if the force acting on it are conservative. Gravitational force alone acts on it. Only if elastic force alone acts on it. For any kind of force act on it, work energy theorem is applicable for any kind of force. That is, fourth option is correct. The next question is, the work done by all the forces, external and internal, on a system equal to change in its kinetic energy. Total energy, kinetic energy, potential energy, none of these. From work energy theorem, work done by all the forces on a system is equal to change in its kinetic energy. Option B is correct. Let's do this problem based on the applications of work energy theorem. That is, a 15-gram bullet is fired horizontally into a 3 kg block of wood suspended by a string. The bullet sticks in the block and the impact causing the block to swing 10 cm above the initial level. The velocity of the bullet is nearly. Here we are going to find the velocity of the bullet, initial velocity of the bullet. The options are these four. Now the solution. Here first we have to apply linear momentum concept, and it rises to the total combined system is raised to certain height, work energy theorem. By applying that to, we derived the formula for bullet velocity, that is capital M plus small m by small m into under root 2gh. What is capital M? Capital M is the mass of the block. What is small m? Small m is the mass of the bullet. H, height raised 10 cm. If we substitute all these in this one, that is equal to 3 kg plus 15 grams. Convert this 15 grams into kg, 0.015 by mass of the bullet, that is 0.05, that is 0.015 into under root 2gh, 2g10 into h. What height it raised? 10 centimeter. 10 centimeter converts into meter, that becomes 0.1. Then after substituting and in further simplification, we get is equal to 3 into 10 power 3 by 15 into under root 2. That is 14 by 5. In simplification, 281 meter per second is the velocity of the bullet.